topic we're doing next. And this is going to lead us into, well, it says there, the differentiation. So considering the calculus for real valued functions. Okay. But we're going to begin with some material looking at limiting values of functions and continuity of functions. Okay. Now, first of all, just to point you towards some resources. So still this book, the Schaum's Outline of Calculus, is still a very good resource for you to use. And as you all know, you can access the full text of that by clicking through the Moodle block, clicking through the library block on Moodle there. You can get through to a PDF, to an online copy of that book. And also in the further reading here, it lists a couple more ones, relevant ones here, engineering maths and modern engineering mathematics. So those are some other two textbooks I recommend that you make use of as well. Okay, so you'll find lots more examples in there, alternative explanations of some of these things. And the Schaum's Outline of Calculus book is particularly good for kind of practice problems, and it's got plenty of worked examples there and practice problems with solutions for you to practice on. Okay. So what are we looking at here? Well, we're going to be studying real valued functions. So functions mainly, or yeah, from the real numbers to the real numbers. These are our real valued functions from the real numbers to the real numbers. But sometimes it might be necessary to exclude. Sometimes we might have a nice, and that's supposed to be an F there, by the way. F. Sometimes we might have a nice function, like here in the notes, there's one like 1 over x. That's a perfectly good function, although, of course, not on all of the real numbers. The function that sends x to 1 over x is perfectly valid for all the real numbers, except you have to exclude a certain element from the domain. You have to exclude 0 because there's no meaning to 1 divided by 0, of course. So on the whole, they'll probably mostly be from all of the real numbers to all the real numbers. But sometimes, as we say, sometimes we need to restricted, sometimes with a restricted domain. E.g., so you could have a function g from r/0, so r without 0, and that's defined by g of x is 1 over x. Or let's say, take the logarithm function. The logarithm function goes from not all of the real numbers, because you can't have a real logarithm anyway of a negative number. So this has to go to r plus, where r plus is the set of all strictly positive real numbers. So it's the set of all real numbers such that x is strictly bigger than 0. Okay. But we still call these functions real valued functions because they're taking their values in the real numbers. Okay. So first of all, we want to talk about limiting values of these functions. So we've looked at limits in the case of sequences and series, and the same concept passes through to talking about functions. So we talk about the limiting value of a function, but now we're not taking a limit as n goes to infinity, where n was the index of the sequence term, or taking the sum of the sequence term over all the sequence indexes as n goes to infinity, because this time we've got a real argument x for the function. So we take limits like this. So if you see something like this written, this is saying the limit as the argument x approaches the value a, of the function values f of x is equal to L. Okay? Or the limit as x tends to a of f of x is equal to L. Or there's an alternative kind of notation, just using the arrows without using the limit operator as such. So just saying f of x tends to L as the argument x tends to a. Okay. And informally, you know, it's the same idea as we've seen before. We say, you know, what this is saying is that the function f is getting closer and or the function values f of x are getting closer and closer to the limiting value a as the argument x gets closer and closer to the limiting argument a, if you like. Okay. Now this description, it doesn't make any explicit reference to the actual value of the function at f of a. Okay. It just refers to the behavior of the function as f of x gets closer of f of x as x gets closer and closer to a. Okay. So it's worth just emphasizing that point. So saying that f of x tends to L as x tends to a makes no reference to the value f at a. Okay. It just refers to the behavior of the function f close, or the behavior of the values f of x close to a, but not actually at a itself. Okay. But now we need to enhance this notation and enhance the way we talk about limits a bit, because it's not sophisticated enough, or it's not detailed enough yet to handle situations like this. So here's a kind of a funny function. It's it's made up of, or its graph is made up of the union of these two straight line segments coming on this straight line here as you approach one from the left, and moving along this line as you move away from one on the right. And the actual value of the function at one itself is specified somewhat arbitrarily at the value 3. So everywhere less than 1, the function takes values along this line. Everywhere for x strictly greater than 1, the function is taking values of x along this other line. And at 1 itself, the function takes the value 3, somewhat arbitrarily. So we can see what we can see here is two different limiting values as the argument x gets closer and closer to 1. Okay, because it depends how you approach 1, how you get closer and closer to 1. If you just approach 1 from the left, so you approach 1 by getting closer and closer to 1 through values that are strictly less than 1, then the limiting value of the function f is going to be 2. Okay, because that's the 2 is the number that the function values get closer and closer to as x gets closer and closer to 1, but from the left, or from the values less than 1. However, as you can see, if you converge to 1, or if you let your argument x get closer and closer to 1, but from the right-hand side, so through values strictly greater than 1, then the limiting value of the function you're seeing is 4. Okay, because the function values are creeping up here, and they're getting closer and closer to 4. Okay, so you've got two different limits depending on how you approach the argument 1. These are sometimes called the left-handed limit and the right-handed limit. Okay, and neither of them are equal to the value of the function at 1 itself. And you can arbitrarily redefine the value of f at 1 to be any value whatsoever, and it won't affect the limiting behavior of the function as x gets closer and closer to 1. Okay, so in order to accommodate talk like that, we enhance the notation like this, so we can say the limit as x approaches a, but with the a superscript minus sign there. So that's referring to the limiting value as you approach a from the left. So through values, well, from the left meaning through values that are strictly less than a. And if you approach a through values that are strictly greater than it, we write that as the limit as x approaches a plus. And we can also bring infinity into the notation in various ways. Now, I must pause and emphasize that infinity is not a real number. Of course, it's not an element of the real numbers. But we can bring in the symbol infinity anyway to describe how functions might be behaving. So, for instance, if a function f is growing without bound as x approaches some argument a, then we might write something like this, that the limit as x approaches a of f of x is equal to infinity. That would be, well, is it equal to infinity without a minus sign? That would be implying that the function f is growing and growing in positive absolute value. Okay? So getting larger and larger in the positive direction. So there's an example here shown about the function 1 over x. Do I have the graph of 1 over x? Yeah, so there's the graph of 1 over x. And you can see that there's something funny going on as x approaches 0. If you approach 0 from the left, the function 1 over x is getting larger and larger in absolute value, but in the negative direction. And if you approach 0 from the right, the function 1 over x is getting larger and larger in the positive direction. Okay, and there's no upper bound to how large it can get as you get closer and closer to 0. So we can express that in the limit notation as saying the limit as x approaches 0 from the left of 1 over x is minus infinity, and the limit as x approaches 0 from the right of 1 over x is equal to plus infinity. And you can also bring the infinity symbol into the argument as well, and say things like the limit as x approaches infinity of f of x is equal to L, and that's referring to the limiting behavior of the function as the argument gets larger and larger in absolute value, okay, in the positive or the negative direction accordingly. So sticking with this function 1 over x, you can say that the limit as x approaches plus infinity of 1 over x is 0. Okay, so as you let x get larger and larger in the positive direction, the function 1 over x is getting smaller and smaller, and there's no limit to how small it's going to get. Okay, but it's always strictly positive. It's just getting closer and closer to 0. So the limit as x approaches infinity of 1 over x is 0. But if you go out the other direction, if you go to larger and larger negative arguments, 1 over x is still getting closer to 0, but this time it's getting closer to 0 from below. But it's still getting closer and closer to 0. So we can say the limit as x approaches minus infinity of 1 over x is 0. So there's various ways we can use this limit notation and limit operator. But we're still only talking about the concept kind of vaguely or informally, using this idea of the values getting closer and closer to some limiting value as the argument gets closer and closer to some limiting argument. We'll firm things up and make things a lot more rigorous and formal when we meet the definition of continuity, and then we'll introduce the kind of more formal, exact, detailed definition of continuity, which will need to be able to prove things about how this limiting value concept behaves when you look at sums of functions or products of functions and so on. But sticking, without going down to that formal level yet, we can observe that we have a very similar algebra of limits result for functions that we did for sequences. Okay. So the functions in this sense are behaving in a similar manner to how convergent sequences behaved. And in some senses, you can kind of regard functions as a kind of continuous version of sequence. The sequence is kind of a discrete object. You've got one term of the sequence here, and here's another one, here's the third one, there's the fourth one. They come in discrete kind of chunks. Functions or real valued functions, functions defined on the real number line aren't like that. They have, the real number line is, you've got elements of the real number line all along it. They're everywhere. They're all pervasive along it. The number line can be infinitely subdivided. But you can kind of envision it and think of it as a kind of continuous sequence. So instead of having a discrete index n for the sequence element, x1, x2, x3, x4, up to xn, you've instead got a continuous indexing element, which is coming from the real number line itself. So f of x is the sequence term, supposedly, and x is the indexing element. So when you think about it that way, there's a kind of a strong connection between sequences and functions, real functions on the real numbers. Okay, so these results about limiting value look almost, it's almost as if I've copy and pasted them from the similar result for sequences. There's one for linear combinations. So if you have a linear combination of two functions, okay, alpha times a function f plus beta times a function g, so you can consider that as a third, or as a new function. So given functions f and g, which both go from the real numbers to the real numbers, we can form a new function where you take two scalar values, alpha and beta, and then you have a new function, alpha times f plus beta times g. And this will again be a real valued function defined in the real number line, okay? And then the question is, well, if these two functions f and g had limits as x approaches a, is this new one that you've constructed going to have a limit as x approaches a? Well, the answer is yes, and it has the only limit it could have. So f has the limit L, g has the limit n, as I've set it up here. And so the limit of alpha times f plus beta times g as x approaches that same limiting argument a is going to be alpha L plus beta times n. Okay, so you can kind of, and the same result for products. The limit of the product, f of x times g of x, is equal to L times m, and the limit of the quotient, or the ratio, f of x over g of x, is equal to L over m. Provided that the m is not zero, and you probably need a bit more there, that the function g, just that the function g avoids zero in the neighborhood of the limiting argument a, just so that you don't run into any problems with it dividing by zero. Okay. So in this theorem, theorem 4.1, and we're not going to prove it formally. I'm going to reserve the formal proofs for when we're looking at the related idea of continuity. But so you can easily summarize these results, summarize or remember these results I mean, you can remember them in English, really, or whatever the language is. The point is not to get so attached to the symbols all the time and to always think in terms of symbols and think that that's what maths is. Mathematics is about the ideas which are lying behind all the symbols, and the ideas are quite easily expressed quite efficiently, because the first property there, well, the thing on the left-hand side is the limit of a linear combination. of functions implied. But the result is saying that the limit of the linear combination is the linear combination of the limits. It's almost like a tongue twister in some senses, but it's like a really quick thing that distills the essence of what's being said here. The limit of a linear combination is the linear combination of the limits. And the second one about products is saying the limit of the product of functions implied here. We're talking about functions. The limit of the product of functions is the product of the limits of the two functions. And the third one, the limit of the quotient is the quotient of the limits. Limit of the quotient is the quotient of the limits. So each result is you know, they're all structurally very similar results and structurally almost identical to the similar results we looked at for sequences. But the limit of a linear combination of two sequences was the linear combination of the limits. But the limit of the product is the product of the limits. But the limit of the quotient is the quotient of the limits. Of course, don't be misled that everything in mathematics behaves so nicely. You've already seen, and you will see more, you know, probably the more interesting mathematical things or often the more important mathematical concepts don't behave so easily necessarily. And that's what kind of makes them interesting, and that's what reveals kind of or suggests that there's a lot more going on when they don't act so easily. For instance, in linear algebra, you've seen the notion of a matrix determinant. So just compare these ideas, compare these with the matrix determinant. Now you have seen, you will, I mean, how do I complete this formula? The determinant of A times B. From your linear algebra work with matrices. What's the determinant of a product of two matrices? You have covered determinants, haven't you? Yeah. You have, yeah. So yeah. Someone shout it. Someone be brave. Given what's on the page above it, what would you shout out? The product of the determinants, yeah. Which it exactly is, which is correct. The determinant of a product of two matrices, as long as the product makes sense, as long as the matrices are compatible, that you can multiply them, the determinant of a product will be the product of the determinants. But be careful, don't be misled. Very careful, right? If you weren't being careful, you'd be tempted to say the determinant of a sum, which is a linear combination, you'd be tempted to say that that's the sum of the determinants. Now, I even hesitate to write it down, just in case I plant the idea in your head, but this is not true. Might be true for some special pairs of matrices, almost by fluke, but it is not true in general, okay? So the determinant of a product is the product of the determinants, but the determinant of a sum is not the sum of the determinants. So, you know, things don't always work so nicely, but when they do work nicely, when they do have this, when the results do have this nice, really simple structure, it is really useful because it allows you to remember it very easily and allows you to kind of draw connections between the results you're looking at and other similarly structured results. Okay, so you can say there that the determinant of a linear combination of matrices, it's implied, determinant of a linear combination is not, in general, the linear combination of the same linear combination of the determinants. So that's kind of bad in some ways because it means determinants aren't so easy to work with necessarily. But it's also good in that it reveals that, well, determinants are more complicated, is a more complicated concept, perhaps, than the limiting operator of a function in this sense. So it means there's more to study there. There's kind of more to understand, perhaps. Okay. Okay. So I encourage you all the time, like when you meet new results in mathematics and you meet new ideas, new concepts and facts about them, you know, always be looking for these kind of more structural ways to think about them, rather than getting attached to whatever the notation is, okay? Because, you know, another author might well write down these properties for the limiting values of functions using completely different symbols and completely different notation, okay? So it might look completely different on the page, but so, you know, trying to memorize these properties in terms of alpha F's and beta G's is perhaps not the best way to go about it. You're much better off understanding or appreciating this kind of more fundamental version of the results, of the structure of the result, okay? Because you can easily then write down, you can easily reconstruct the result in symbols just by deciding, okay, well, the limit of a product of two functions is the product of the limits. Okay, so I got to give a name to one function, a name to another function. I got to name the limits that they have. And then you'll be able to reconstruct some version of that middle equation up there to give the result in mathematical notation, okay? And, you know, appreciating this kind of difference, say, with the behavior of the determinant is good because, you know, keep it in your mind that determinants are kind of slippy, kind of tricky kind of things to work with. Sometimes they behave really nicely. The determinant of a product is the product of the determinants. And, you know, in terms of matrix powers, the determinant of a matrix to some power is just the determinant raised to that power. So the power operation slips in and out of the determinant really nicely, but not for sums. Determinant of the sum of two matrices is not the sum of the determinants, okay? So when you think of things more structurally like this, you're more likely, I think, to remember these exceptions and to remember, you know, when mathematical objects have these nice properties and when they don't, because it's a lot easier to, you know, so in the mathematical notation, this would be perhaps written like this: determinant of AB is equal to determinant of A, determinant of B. If you're just focusing on the notation, the notation all the time, it's all too easy to kind of think, well, obviously the determinant of A plus B, well, it works for that, so why doesn't it work for this? Yeah, but it doesn't, of course, it doesn't. So I think you're more likely to kind of spot these things and remember these things and be aware of these differences of behavior when you're thinking about the results in a kind of structural way like that. Okay. So that was kind of like a detour a bit. So on a kind of basic level, we can use these results about the behavior of the. So what's there going on? It's talking about the behavior of the limiting operator with regard to the operations we can do with functions. And it's saying that the two mesh together very well, the limiting operator and the arithmetic operations we can do with functions. And they're the kind of results we can use to figure out limiting values of more complicated functions in terms of the limiting values of the kind of simpler components of the functions. And I just want to highlight the existence of L'Hopital's rule again. Now, it feels a bit funny talking about this here because L'Hopital's rule talks about the derivative of a function, and this whole chapter is leading up to the definition of the derivative and working through its properties. But I think most, if not all of you, have worked with differentiation before. You're aware of it. So we'll just kind of use it as a little bit of a tool at this stage, just for working with function definitions. But we'll be going through the theory of the derivative and its properties in due course as well. So just to remind you, L'Hopital's rule tells you how to work with limits of quotients when, if you just take the limit, if you just take the quotient of the limits, if you're looking at the limit of a quotient of two functions, and if you just rush straight ahead and take the limit of the top part and the limit of the bottom one, so the limit of the numerator and the limit of the denominator, if you're seeing then a quotient like this, 0 over 0, or infinity over infinity, well, you can't resolve those into quantities just like that. The quotient of the functions, if you see this, 0 over 0 or infinity over infinity, well, it could still be a convergent quotient. It could have any particular limit, or it might be a divergent quotient. You can't tell just by observing what the limit of the numerator is and what the limit of the denominator is. So if you reach a form like this, you can't really draw any conclusion about what the limit is. But L'Hopital's rule can often help, and that says that what you can do is you can pass to the quotient of the derivatives instead. So rather than looking at the limit of the quotient of the original functions, you can look at the limit of the quotient of their derivatives. Okay? And if this one has a limit, if the new quotient has a limit, it will be the same limit as the previous one had. Okay? So you can use that as a way to evaluate limits, or as a tool to try and evaluate limits of more complicated functions. Okay? We'll be seeing a proof of L'Hopital's rule once we have a kind of full detailed view of what the derivative of a function is. Okay, so we could just finish perhaps by just having a look at some of these examples and see what's going on here. I mean, they're mostly worked out there, but I'll just talk through a few of them. And there's a set of exercises in the end of chapter exercises based on these kind of problems. So let's look at this first one. So the first one is saying the limit as x tends to infinity of 3x plus 1 over 2x. So what's going on there? Well, again, you can't just simply evaluate the limit of the top part and evaluate the limit of the bottom part, because they both tend to infinity as x tends to infinity. So as I've said, infinity over infinity, this doesn't refer to any kind of quantity, could be anything. So, but we can use a similar idea here to what we used for when we were looking at sequences. We can divide above and below by x. So let me just write that out just to indicate what I'm doing. So we're going to divide the top by x and divide the bottom by x. Okay, and we're perfectly free to do that. X is just a real number. We're dividing above and below by some same real number, so we're not changing the quantity, but it does change the description of the quotient. It's now the quotient of 3 plus 1 over x over 2. And now we can use the quotient form of the algebra of limits result, because the top one does have a limit and the bottom one does have a limit. Okay, so this you can now say is the limit of 3 plus 1 over x divided by the limit of 2. These are all as x goes to infinity. Well, the constant 2 doesn't change as x goes to infinity. It's always at the value 2. And the top part, well, you've got a constant plus this part, the limit of 1 over x, but as x goes to infinity, that goes to 0. So that leaves you then with the final limiting value of 3 over 2. So just to put in the comment here at the top, we can't apply the algebra of limits result yet. I mean, we applied it here when we went from the limit of the quotient is the quotient of the limits. We can't apply it at this stage yet, as the numerator and denominator both go to infinity. Here's quite a well-known result, quite a famous result, or quite an important result for the development of a lot of results in calculus. And we can appreciate it at the moment by seeing it as an application of L'Hopital's rule. But that's not really how we should see it. You actually this needs to be proved really to do it justice, to be proved with a geometric argument that works with, what sine, of course, refers to the quotient of the opposite side from an angle over the hypotenuse of the triangle. So we really need a geometric argument to evaluate this limit. But we can kind of see it as an interesting application of L'Hopital's rule at the moment. But again, the same kind of comment applies here. You can't just say it's the limit of the top part divided by the limit of the bottom part, because both are zero. Okay. Sine x, remember, goes something like this. There's pi over 2, there's 1. So the limiting value as x approaches 0 of sine of x is clearly 0. And the limit as x approaches 0 of x is 0 as well. Okay. So you can't use the algebra of limits result, but we could apply L'Hopital's rule. That says the so we could say d dx of sine of x over d dx of x. And so this then would be the limit as x approaches 0 of cosine of x over 1. And a cosine of x, that's some function like this. One that reaches 0 or pi over 2. This is cosine of x. So cosine of x does have a nice limiting value as x goes to 0. It's just got the limiting value 1. So you can say that's the limit as x approaches 0. Cosine of x, which is 1. Okay. But actually, we need to see a geometric proof of this more from first principles, from earlier principles, so to speak. Because we're using here a result which you're probably all familiar with, that the derivative of sine of x is cosine of x. But the question is, how do you actually prove that the derivative of sine of x is cos of x? Actually, the limit, in most ways of treating it, you actually need to know the limiting value of sine of x over x in order to prove, I think, that the derivative d dx of sine of x is cosine of x. So we're kind of doing it backwards here. We're kind of using that result, using the known derivative of sine of x to say what the limit of sine of x over x is. I think more historically, or being more faithful to the way the subject develops from first principles, we should rather do it the other way around. Okay. So at the appropriate time, I'll try and talk you through, and I'll try and show you the argument for establishing this limit without appealing to the use of L'Hopital's rule. Okay. Then just to end on this note, just to draw your attention to something like that last exercise there. So that last one, number 6, the limit as x approaches 0 of sine of x minus x over x cubed. That's another example where we're using L'Hopital's rule, but it takes a number of applications of L'Hopital's rule. That takes 1, 2, 3 takes 3 applications of L'Hopital's rule before you arrive at a quotient which has a limit. Okay. The second stage here, you've still got a 0 over 0 thing. And the third stage here, you've still got 0 over 0. So you can keep applying L'Hopital's rule as many times as you want, providing the derivatives exist all the time. And if after a finite number of steps, if you do get to a quotient which does have a limit, so that happens here, you've got minus cosine of x over x. If that limit exists, so here it's minus a 6, then that indeed is the limit of all the earlier quotients as well. Okay, so you may require a few applications of the L'Hopital's rule result. Okay, I'll finish there for this morning. Remember the class test in the last week, and watch your inboxes today. I'll send around the arrangements about who goes where. Okay.